Good afternoon to everyone. I am glad to introduce our today's speaker, Dr. Aditya Paranjape, to our audience. Shri Aditya Paranjape received BTech and MTech in Aerospace Engineering from the Indian Institute of Technology, Bombay in 2007 and PhD in Aerospace Engineering from the University of Illinois at Urbana-Champaign in 2011. After completing his postdoc in 2013 from the University of Illinois, he held tenure-track academic positions, most recently at Imperial College, London, before spending 5 years with the TCS Research in Pune, India. So we are privileged to have you, sir, in this lecture. And we will be, today's topic is quite interesting because of the recent incident about the flight 171. And we are happy that you will be analyzing it. Over to you, sir. Thank you.
What I'm sort of hoping to do in this talk very briefly is to show you how you can construct a flight trajectory using basic laws of physics. This is stuff you know. Things that you can derive, but also considering that some of you may not have been in an aerospace background, I hope this is instructive for you. And I wanted to just maybe talk a little bit about flight systems, but as I realized, you cannot have that discussion without a very specific context. So I'll just show you a little bit about the engines, but I'll talk more than I'll show. And if you ask me questions, I'll be able to give you more details. So we'll keep that second part more Socratic. The first part will be, like any formal presentation, I'll show you the equations, show you figures, and show you some estimates that have come along. And I'm sure there'll be a fair bit of time. So I'll also show you a little bit of a small computer code that some of us, that at least I put together with those equations. And I'll let you even, just tell me, and I'll play around with it, and I'll show you what kind of scenarios emerge when we try to model the flight of AI-171. So that will also make it a little more interactive. It's not a Jupyter notebook, so I can't kind of share it. It's sitting currently on my computer, but I'll be able to show you that as well. And like I said, there'll be no speculation, no apportioning blame. This will be a 100% technical talk. We just analyze the motion of that vehicle, and that is all we do. All right, so let's get started. Okay, yeah. So you have lift, which acts, I'll show you exactly where it acts, but it helps balance the weight. And as a consequence of producing useful lift, the airplane also produces drag, which is what thrust helps to which thrust helps to counteract. So the force balance just tells you that, lift and weight have to balance each other out. Thrust and drag have to balance each other out if the airplane is going to fly in a straight and level sort of a flight. So it turns out, so in aeronautics, we have a fairly rich history of working with dimensions and dimensionless quantities in particular. So any aerodynamic force or moment can be written in the form that I've shown here in these equations on the right-hand side. So lift, for example, is written as the product of the density of the air, the speed of the airplane relative to the oncoming wind, and square of it. S is some reference area. So typically, we take the wing planform area, and this product, 1/2 rho v square here, it has the dimensions of pressure, so it's called as a dynamic pressure. When you multiply it by the area, you get a force. And so that last term that remains here, CL, is dimensionless, and it's called the coefficient of lift. In a similar vein, we write out drag in terms of the dynamic pressure, the area, and the coefficient of drag. All right, so that's the absolute most basic primer. Just bear in mind, CL and CD are going to make an appearance a fair bit as we go through the talk. All right. Okay, I'm not able to change slides. No, there you go. All right. Now that same force balance equation actually becomes a little more nuanced. I showed you an airplane flying straight and level. Now, instead of flying straight and level, if our airplane's climbing or descending, here's what happens. So I have an airplane now that's climbing or descending. And this time around, well, when you ask, what do you mean by climb? Where is the airplane pointing? We have to be a little cautious. So the first thing we do is we draw this kind of a reference line. Think of if the fuselage were a perfect cylinder, this black reference line would be the central axis of that cylinder. It's called the fuselage reference line, or the FRL for short. Now, the FRL is inclined to the local horizon, and the angle between the FRL and the horizon is called as a pitch angle. Okay. Now, the pitch angle is basically only used to sort of identify the component of the gravity along that line, but it's irrelevant to our discussion today. So we won't worry about the pitch angle. But what we'll worry about are two specific terms that add up to the pitch angle. Now, it's understandable that the airplane's velocity vector or the flight path, which is shown here with this black arrow, need not be perfectly aligned with the FRL. That's obvious. Sometimes the plane's nose can be above the velocity or sometimes below. And the angle between the velocity vector and the FRL is known as the angle of attack, denoted by alpha. And that second component that tells you, the angle at which the airplane's climbing or descending, which is measured by the angle between the flight path and the horizon, that angle is denoted by gamma and it's called as the flight path angle. Okay. Now, if you were to just adjust the equations of motion, because what happens is, as a matter of notation, lift and drag are defined along and perpendicular to the velocity vector, that is to the flight path. So lift is perpendicular to the flight path and drag is by convention along the flight path. If you make some of these adjustments, turns out that the equations for equilibrium motion with the airplane climbing at gamma can be written in the form that you see here on the slides. It's a minor adjustment. But what I've also had a chance to do here in this slide is to introduce two symbols. The first is a flight path angle gamma, which is obviously a measure of how steeply or the airplane's climbing or descending. And we've defined the angle of attack alpha. Okay. These angles are important, alpha especially, because it turns out that the coefficient of lift and the coefficient of drag CD depend exclusively on alpha as long as the airplane's Mach number is not too high. So if the Mach number builds up, there's an additional dependency here, but otherwise CL and CD are driven exclusively by the angle of attack. All right, nothing else. And that's sort of obvious because the aerodynamic forces do not depend on gravity. They really just depend on how fast the airplane is moving with respect to the ambient conditions. And so whatever orientation the airplane has with respect to the oncoming wind, that's all that's going to dictate the forces. And that intuition is captured here in these mathematical expressions. All right. So with that, let's understand what CL and CD, the two coefficients, look like as a function of alpha. And that's going to lead me to talk about a phenomenon known as stall. So it turns out that the coefficient of lift, CL, as a function of alpha, has a very distinct bound. So if I were to plot CL versus alpha, I've shown it in green. It initially increases linearly. This reference value need not be 0. It could be some other value. It depends on the shape of the wing, precise shape. And then after a point, it flattens out. And when it flattens out, you get a condition known as stall. Now, what's happening physically is that on one side of stall, that is where the lift increases linearly with alpha. If you look at this picture, you will see the flow around an airfoil. This is, by the way, taken from a wind tunnel. And you see that the flow actually smoothly tracks the profile of the airfoil. So that flow is called as attached flow. And that attached flow is what enables this wing to produce a good deal of lift with the penalty of very little drag. So to give you an idea, this ratio between the lift and the drag is typically as high as, for a pure wing, not counting the fuselage, that ratio is as high as 30 or 40. When you add a fuselage, that ratio obviously comes down. Now, once the reason why this stall happens is because this flow struggles to stay attached as this wing starts becoming more inclined with respect to the oncoming flow. And what you see on the right is another picture from a wind tunnel. And now you notice, this is of course once the airfoil is already stalled and gone a few more degrees beyond stall. You notice the flow streamlines no longer track the airfoil. In fact, there's this huge region in between where you don't see streamlines at all. And that region is known as a wake. And in that region, the flow has separated fully. And the problem with this is the lift drops, which is fine, but a drag goes up substantially. So whereas here, for example, in the linear regime, while you enjoyed lift to drag ratios of as high as 30 or 40, here they start to drop. You're down to 10, 5, and at sufficiently high angles, drag starts to dominate lift entirely. So that's the reason why stalling is a fairly serious problem. But that is not it. The problem is once the airplane stalls, that angle of attack alpha, which sort of dictates stall, is no longer fully in your control. In fact, it continues to increase, lift continues to drop, drag continues to go up, and as a result, the plane actually starts to plunge down. And occasionally, even had it ended there, it would have been okay. But it also turns out the airplane starts developing other form of instabilities and it typically starts to spin. And once it enters spin, it's not easy to recover it. So some airplanes are resilient to spin. Some can occasionally recover on their own, but they have to be designed for that. But in a lot of cases, this spin can be fatal unless you start a spin at a fairly high altitude And then if you have a trained pilot, they can recover the airplane. But usually this is where you have problems. So back in the day, when spins were first discovered or rather observed in flight around the time of the First World War, these spins were called takeoff spins and landing spins. The role of stall in creating spins at that point wasn't appreciated, but that's how common they are. Now, the key point here is stall depends on the angle of attack alone, period. Now, some of you who've been enthusiastic about aviation may have heard this phrase stall speed come up every now and then. The stall speed is actually that speed at which if the airplane were flying straight and level in equilibrium, then it would be at this peak CL, that is at the alpha stall. That is all that stall speed is. The question is, between stall and stall speed, are they equivalent? They are not. So what we mean specifically is that airplanes can occasionally go under the stall speed safely as long as they do not demand that lift be equal to weight. All right. So the reason why I brought this up here specifically is because going back now to Air India, to the flight. I'll play the video for you later, and also show you why it was thought of as a stall. But there was a feeling maybe that the airplane had stalled, and some of us on the other hand held firm saying that it's not a stall, because when an airplane stalls, the rate of descent is huge. It's typically on the order of 4,000 to 5,000 feet per minute, sometimes even higher. Whereas with Air India, we saw a much lower descent rate. So we knew the airplane hadn't stalled. The speed can go down below stall, like I said, as long as the lift stays below the weight. And when that happens, the airplane is no longer flying straight and level. It's actually performing a turn in the vertical plane. So its flight path angle is getting ever steeper, but it's still under control. All right. If you now throw in an energy calculation, which is also, again, fairly interesting. Remember, we do know that the speed recorded was around 180 knots at 21 feet. 21 feet we can assume to be zero for the sake of argument. All right. Now, if you just decide to look at energy conservation, forget drag for just 1 minute, but you can compensate for it fairly easily. It tells you that the max altitude that the airplane attains will depend on the speed. At this point, it is not known. But if you use something like 170 knots, which is the value that was recorded at some point by Flight Radar 24, you get a max altitude of around 150 feet AGL. Numbers can vary, so that number could be as low as 120 if that 170 shifts to 172 or 173. It can go up slightly if that 170 drops down to 168. So that's the ballpark that we are looking at. So we get very different estimates in there. So this is the first part of how you go about sanity checking the trajectory that you've got. The second thing that some of us tried to do, so it was me. There was an Air India engineer. I won't name him here, but he's fully rated on the 787. So we just sat together and decided to do some estimates. And what we did was, if I may just go back a few slides, we coded out these equations. I was going to show you some plots, but I thought I'll show you the code itself directly. And if you want, we can even play around with it. Is anyone interested in playing around with the code now, or do you think it's not of much interest? Sorry, I can't see anyone. So if you're interested, just speak up. If you think it's not of interest, we can move on. But you need to tell me something.
We'll run the codes towards the last part, sir.
Yeah, sure. You want to do that? Okay. So towards the end. So I'll show you then how the code works. The point about the code is not the code itself, but what I want to point out is the difficulty that's involved in modeling this. So you remember I told you earlier about the coefficient of lift having to be delicately managed. That's something I pointed out. And that point will become amply clear. And so you'll actually see what CL can do, what kind of policies you can use, and so on. All right. So let me just stop there for one moment. Does anybody have any questions about the trajectory modeling that we've done so far?
Yeah. I have a question, Dr. Paranjape.
Yeah.
You I was telling about the descent in a gliding mode. I mean, after the reaches height, the flight descended in gliding mode. But what if, I'm speculating, because of the angle of attack was at above a particular way, the drag would have been much higher, and it would have not been a gliding, right? It would have been a downward force, which would have forced down more forcefully than a gliding.
Oh, no, not at all. No. Actually, the plane was in gliding mode. That's one thing we were trying to determine the exact point where the thrust was lost based on trajectory estimates. But the plane was pretty much in gliding mode from just a few feet above the ground. Now, in airplanes of this sort, regardless of the angle of attack, the drag is high. But even when the drag is high, the lift is high as well, unless your angle of attack shoots up. And these airplanes, two things happen. First off, pilots are trained to not get the angle of attack above a certain critical value, which is about a few degrees below stall. And these airplanes have a very well-developed envelope protection system, or EPS for short, which prevents the angle of attack from exceeding the stall value. So if stall is not exceeded, your CL by CD ratio or your lift to drag ratio will stay at a reasonably high value. It may not be the optimum value of whatever 19 or 20, but it will not plunge down to the stall kind of values either. And so consequently, what will happen is you may not get a steady glide. You may lose speed because the pilot's still maneuvering the airplane, but you will get something that resembles a steady glide as compared to a fall.
Okay. Understood.
So in fact,
Understood.
So what happened with Air India 171 specifically was one of the recordings was taken by a boy in a settlement right beyond the airport. And in fact, if you were to look at that video, that you can clearly see the airplane just gliding down. So that in fact was one of the first signs that this wasn't a stall. And in fact, okay, if it's okay, let me just see if I can play that video very quickly for you. So I'll be able to show you what I mean by that. Notice the airplane climbing up. It flattens out around this time. So around 14 seconds, flat, almost flat, and it starts descending here. Now, as you watch this descent, you'll notice here the airplane wings are by and large level. It's very difficult to tell, of course, if the rudder or the aileron were used from this distance, but we know from other videos that they were rarely used. And this kind of a profile is not consistent with a fall, because if the airplane were to start falling, that would be only because of stall. And when stalls happen, the airplane will not fly with this kind of a wings level configuration at all.
Yeah.
It's almost impossible for the airplane to do that. So once a stall happens, it can be very aggressive. What I was going to talk to you about was the engine control. Now here is where, I have to admit, I'm not an expert. This is one place I realized I've sort of got a lot of things from engineers. Of course, knew a little bit about it myself as well. But one question that we were generally trying to understand, and this was a question that also probably people asked for a number of different reasons, is how do the engines fail in the first place? Never mind how do two engines fail. So just want to give you a bit of an idea. Some of you may have already read about it or heard about it even in the press. Some of you may have followed it up with other sources. But I thought I should just tell you a little bit about what happens in general. Okay, so if you look at an engine, now this is a cutout of the GE engine that's used on the 787. There are a few parts that we should highlight. First is the fan. This fan is a low pressure fan, and the flow behind the fan splits into two channels. There's one channel that goes through without any further processing, if I may call it that. It's called the bypass. It goes to the outer duct here. It's relatively cool air, and there's some air that enters this area with these rotors that you see here. This central area of the engine with the rotors and such is known as the core. The core itself consists of three major sections. You have compressors. So the compressors here they come in two stages. There's a low pressure compressor and a high pressure compressor. Then you have a combustion chamber, and followed by a two-stage turbine. So low and high pressure again, other high and low pressure, before the air is vented out at a reasonably high speed. That's the usual structure of an engine. Now, what all is actually measured, what all can fail? Well, the first thing that is measured is the pressure ratio. So the first thing that they look at when they look at this engine is the pressure ratio between the ambient air here and at least 2 points here in the area where you have the compressor. That's called as the engine pressure ratio, or the EPR. That's between the area outside and at the end of the high pressure compressor. The second thing they look at is the exhaust gas temperature, which is the temperature in here at the outlet. They'll also want to see the temperature inside the combustion chamber. And actually, you would have heard of the FADIC, called as the Full Authority Digital Engine Control System. That actually regulates some of these values directly, primarily by maintaining the fuel flow rate at the correct value and thereby producing also the right amount of thrust. Now, what can go wrong in engines like these is as follows. Fans are not particularly stressed in terms of pressure ratios, but these blades are actually fairly stressed, and not because they're going at very high RPMs, but these blades have a very intricate design meant to maximize thrust. And so some of these blades can occasionally snap. If a blade snaps, the engine should ideally be able to contain that damage. This actually never yet happened as far as I know on two engines together. Problems start further in now. one of the most common problems in engines is known as compressor surge. So the problem is this. At this point, just before you enter the compressor, the fan would have amped up the pressure by a factor of maybe 2. So you have 1 atmosphere here, maybe 2.5 atmospheres here. Now from that point to the end of the high pressure compressor, if I'm not mistaken, the pressure ratio goes up to around 30-ish. I don't know these numbers off the top of my head, but they're somewhere in that ballpark, between 25 and 35 or so. And what's happening now is that you have all this air that is being pushed in, and the tendency for this air is to actually go from high to low pressure. So it's trying to go out rather than go in. And sometimes that can become unsustainable, and consequently, the air starts to actually get pushed out because of this pressure ratio. It cannot be sustained. That phenomenon is known as a compressor surge. It's a dynamical instability, very well studied. And when an engine surges, it's pretty violent. It typically needs to be shut down. And it's happened on enough occasions in the past that the plane can make a safe recovery. You just keep climbing with the remaining engine, leave this engine off, dump whatever fuel you have to dump, and come back and land. Right? That's pretty well known. Another problem, sometimes your flame isn't sustained inside the compressor, inside the combustion chamber for some reason, and so the engine flames out. That's problem number 3. So blades can snap off. They can actually even snap off in the chambers inside, or even in the turbines, which are thermally stressed heavily. You can have engine surge, and you can have issues with flame out in the engine. Now, it could really be any of these. The problem with AI-171 was it happened in 2 engines. Whatever has happened has gone wrong with 2 engines, and these are statistical phenomena. See, for the most part, these are not systemic, and as a result of that, the probability of 2 engines experiencing any of these phenomena simultaneously or even in pairs is extremely low. That's the real issue. So when you think about the engine, it's very difficult to believe that something's gone wrong with the engine, but it can go wrong. So these are the 3 phenomena that can go wrong. So the question is, okay, so outside of these 3, what else can go wrong with the airplane? So again, we're not speculating, we're just pointing out what can go wrong pretty much explicitly. So if you look at these engines, they are powered by a pretty intricate fuel supply system. The primary supply comes from tanks that are located in the wing. So each engine gets fuel from the tank in its respective from the tank in its respective wing. In addition, you have a center fuel tank, and all these tanks are connected by a fairly complex set of pumps and valves. So I just asked ChatGPT to give me a picture that I could show. It gave me a text image, which was really pretty neat, I thought. But here's loosely what's going on. So let's say you have a wing tank. You have boost pumps that go to one valve. From here on, I honestly don't know what the spar valve is, other than the fact that it's located in the wing spar. From there on, you have this fuel shutdown valve called as FSOV. It's called the engine fuel shutdown valve. This is one of the more critical valves in the system. And from there on, it enters the combustion chamber. Now you notice the control for both the spar valve and the FSOV come from the switch that's located in the cockpit. But the FSOV in addition is also controlled by the FADEC, which is the full authority digital engine control system. And while the FADEC responds to signals from within the engine, see, the idea is you don't want the primary flight control system to bother about what's going on in the engine. So there's a problem with the EPR, the engine pressure ratio, the FADEC can respond to it without bothering the primary flight control logic. But if something relates to the motion of the airplane, for example, the airplane's altitude, the airplane speed, or the thrust requirement that's commanded by the pilot, at that point, the FADEC gets inputs from the primary flight control law. So if anything has to fail here, it has to be either because of the switch, or because of the FADEC, or because of the flight control law that feeds into it. Now, all of these are generally very well certified, but historically, we do know problems have occurred. And especially the problem is, some of the switches that exist in this system are not mechanical, they're soft switches. That is, they exist in the software. So that's what's actually contributing to a great extent to the uncertainty in AI-171. But anyway, that's the technical side of it. Hopefully that picture will become clear once the final report is out. So let me stop there. Engines thing, we can kind of go on, and at some point I'm going to hit the saturation of whatever I know, which is not a lot. I'm not a specialist in engines, but I've learned a fair bit thanks to talking to some of these very well-informed people over the past couple of months.
Sir, a small question.
Yeah.
This engine fuel shut-off valve you have mentioned is controlled by FADEC and switch. Is it that the FADEC controls the switch, or that FADEC and switch both can control?
It's an AND logic. So if they are both one, the valve is on, If either of them shuts it down, it can shut down.
Oh, okay. Oh,
Yeah.
okay. Because
Yeah,
there
and
were
there's
some
another.
there were some conspiracy theories where somebody has. I mean, it's remotely possible to switch off.
Oh no, sir, no, sir, no, nothing of that sort. That is not that no, there is nothing of that sort. No. So these are completely. It's an AND logic in there. But going a step further, these engines have actually. I mean, the beauty of design is because the way the engines are, these engines are actually capable of sucking in fuel even without the pumps in the system. At least to some fuel flow rate that can keep the engines running. It's remarkable. I wasn't aware of this. I was talking to the engineer and I said, okay, if the valves are off, are we sure the fuel's off? He said that's not true because the engines, see, look, what happens in an engine, I mean, in addition to all the moving parts here, is that you have a massive distribution of pressure across the engine. Okay. And when you have areas where you can have sufficiently low pressure, you can actually suck fuel from, if you have sufficiently high speed flows, that's where the static pressure drops. And if you can connect that to the fuel tank, you can actually suck a little bit of fuel through that suction action directly. That action may not be enough to keep the engine running at its full mass flow requirement, but it might be enough to just keep it idling. And an idling engine is way better than an engine that has shut down, just because of its aerodynamic profile. And an idling engine can be powered up if you go through the recovery procedures. But for an engine that's shut down, you have to restart it, and that's actually a very expensive operation energy-wise. So these engines are remarkably resilient, and the engine and even the fuel control system that goes with it. So even the pumps don't have to run. If it really comes to that.
Sir, it looks a very trivial question.
Yeah.
I want to ask you when the engines will be switched on.
Good question. So the engines are switched on when the airplane is pushed back. So what happens? The sequence is something like this: when the aircraft is pushed back, the pilot first turns on the APU, the auxiliary power unit. The APU is what turns these engines on. And while the APU is also like a small engine in its own right, it cannot turn on all engines simultaneously. So it turns on one engine and the other one sequentially, so that by the time the airplane is fully backed up, and as the airplane gets backed up, it gets pushed back, and at some point the pusher cart is disconnected and moved back. By that point, at least one engine is running and the other engine will be turned on subsequently. That's the usual startup sequence.
No, but
and ideally, sorry, go ahead, please.
No issue. Sorry. Ideally.
Yeah, I can. Yeah. So what I was saying was, ideally, once the engines are turned on at that point, they can keep running as long as there's a source of fuel that they have access to.
No, because I wanted to know whether people of course this is a very trivial question, but whether are you able to make out at that time only that engines are okay or not?
See, the question is, when you say whether they're okay or not, you're probably suggesting a specific type of failure, right? Because if there is no failure, they're okay. So the thing with these failures is as follows. Compressor surges don't happen in idling engines. They typically happen when the engines are powered up, because in an idling engine, the pressure ratios are not that great. But once the engine's running at full throttle requirement, the pressure ratios build up in the engine. So that's when compressor surges are typically likely. Flameouts can technically happen anytime. There is no reason why a flameout can happen only at the start or only mid-flight or there is no systematic reason for it. With blade failures, you expect blade failures to occur when the RPMs are high. So again, when the engine is fully powered up at the time of the ground roll, that's when you expect failures to occur also in the blades. Now, on top of it, if there are any fatigue-related issues, they can of course occur anytime in the flight. The problem is, if there's a fatigue-related problem, it's not checked at the time of engine startup. It's only checked at 2 points: when the airplane goes for when the engine goes for maintenance, and second, when the pilot conducts he walks around the airplane, typically he or she, and they carry out a visual inspection. That is the only check they have at the time of starting the airplane for anything structural. And the other checks that happen when the airplane is started up are electrical checks usually. So there'll be a single button that is pressed in the cockpit. It has a logic to check all of the electrical systems, and if it comes back okay, everything is okay. And then the pushback continues.
But the question is very simple. Unless and otherwise we use the basic technologies, we want now the best one. So kaisa ho sakta hai? It has to be
नहीं होगा, exactly. You're right.
evolving things. So it appears that our defense system, I also in NIS, Niyas Mehta, there some senior, very responsible military officer, got up and told that Indian military or Indian defense system wants the best right now. So that was actually not a palatable stand, because we are having, as entrepreneurs, we have only one customer. Any trials or any upgradation, any evolving has to be done with them only, because it's not like a private or a commercial sector. So they have to allow us to grow, means they have to be content with some application areas where, as you said, second generation, third generation can be first utilized, and think about fifth generation. Right now, I want the best, means then we can safely conclude that they have decided to import. It appears like that. So I
That's
think
true.
a long way to go. Thank you, sir. Thank you.
Okay, thank you. So
Senthil,
Hemant has put something. Can you add some facts on where we stand on flight control system side? I think with LCA, as far as I know, I have not had any contact with the LCA team for 10 years. But at least at that point, they were fairly state of the art in terms of solving flight control problems. That the National Control Law team, for one, has been extremely successful, and something of an outlier, I think, in the scheme, in the sense that they've not just been successful, but they've been very open to collaboration as well. So this is when, Hemant's aware of this, because Hemant was a student when we worked on the on a small part of the LCA control law. So that team has been successful. See, at the end of the day, with control laws, basic control designs are simple, but that group itself, purely as control engineers, they're outstanding, and they've found fixes for a large range of problems on their own. So, for example, the LCA had a problem with an interference between the structural modes and the rigid body modes. So they cracked that problem using a very well-designed notch filter. It's a well-cited paper in Journal of Guidance from the late 90s. These guys did some good work also on controlling spin in the LCA. The list goes on. At that point, there was some talk. We also discussed, the possibility of at some point doing adaptive control on the LCA or one of the future versions. But I don't know what has happened with it. But at least they were asking all the right questions and they were actually doing it. That's the best part. So, Hemant, on the control law side, I'm pretty sure they are doing well.